Hey everybody, welcome to our next problem solving session. As you might have noticed, I'm not in my apartment, I'm actually in lab right now, uh, and I'm aware that there is this kind of high-pitched hum in the background. Uh, Hopefully that doesn't drive anybody insane. Uh, anyway, what we're going to do in this video is look at a couple problems involving impulse and momentum and a little bit of energy. This is, well, all these problems are from chapter 9, and you can find them in the textbook if it's hard to see on the screen. Hopefully not, but so we're going to start with number 38, and I will read the problem statement to you. So in the overhead view of the figure, a 300-gram ball with speed of 6 meters per second strikes a wall at an angle theta equals 30 degrees and then rebounds with the same speed and angle. It is in contact with the wall for 10 milliseconds, right? So that's 10 1,000ths of a second. In unit vector notation, what are the impulse on the ball from the wall and the average force on the wall from the ball? You know, I don't think I actually want to do it this way. What I think I want to solve for is the impulse on... No, you know what? I can read. I actually do want to do it this way. Okay. So for a second there I was confused. So what I don't want to do is part B, actually, because what I would rather solve for is the average force on the ball from the wall, right? Just to keep things consistent. But we can talk about that when we get to that part here. I might not even do it because I think that finding the impulse is the more involved part here, because remember from the impulse momentum theorem, well, we just identified the impulse as the change in momentum, and I think that's what we really want practice with, so let's get started. Okay, so first of all, I'm just going to declare all my symbols, of course. The mass of the ball is 300 grams. That is 0.3 kilograms. Okay. Theta is 30 degrees. Let's say V is 6 meters per second, and then delta T is, well, 10 times 10 to the negative third seconds, right? That's how we would convert from milliseconds to seconds. So let's just write this out a little more clearly. What that should be is, well, 10 to the negative second, right? Which should be just 0.01. Yeah, cool. Okay. So remember that what I was saying is this amounts to really just solving for the delta P of the ball. And this is a two-dimensional example, which is one of the reasons I wanted to do it, right? Because we looked at lots of 1D examples in the lecture, and so now let's, extend that to 2 dimensions. I don't think we'll ever actually even do anything with 3 dimensions, but you could if you wanted to, by just sort of following the blueprint that we're putting out here. Okay, so I'm going to start by saying, well, what is the initial momentum? And I actually don't really like what they did here, where they say both the vectors are v, because those are clearly not the same vector, right? But they're calling them the same thing. So what I would do is I would actually probably call this one v naught, just to be 100% clear. Okay, but they have the same magnitude, right? So looking at this, I think we can see that if we use the x and y directions that they specify, the x component of the initial momentum is positive, right? And that's just given by m v naught, and then it should be cosine theta, but the y component is negative, and that is going to be negative m v naught sine theta. And then note that, right, because the magnitude of v naught is the same as the magnitude of v, we can just write this. Right, that this is mv cosine theta, and this is negative mv sine theta. Okay, cool. Now we just need to do the same thing for the final momentum, right? And this should look very similar because the x component doesn't change. So we can just write mv cosine theta again. But now the y component flips sign, SIGN, right? So it should be positive mv sine theta. And hopefully the plus and minus signs that I've written here make sense, because you can always just look to the figure provided in the problem statement to see what we're calling our x and y directions, and hopefully it's clear that the first momentum vector should have a negative y component, and the second one should have a positive y component. And so now, right, we just want to solve for the impulse. Remember that J is defined to be delta P. And so I think that we probably see that this is P minus P initial. And because the x components are the same for the initial and final situations, then this just becomes 0, right? There's no change. But what we find over here for the y component is actually, well, it's mv sine theta minus negative mv sine theta, which is really just mv sine theta plus mv sine theta. So this works out to be 2 mv sine theta. And so we can say something like this if we wanted to. We can say that j sub x is 0 and j sub y is 2 mv sine theta. Okay. Now I think I'm going to clear everything here because I'm running out of space. So if you still need to copy some stuff down, pause the video and do so, but I'm going to clear it now. And really the only result that we need to take this to completion, as far as I'm concerned, is the j sub y value. So let's write what that was. Remember, it was 2 mv sine theta. And so then, remember that one way of expressing the impulse momentum theorem was that this vector j equals the average force times the time interval, right? And so what we could do is we could just write, well, j sub y equals the average force in the y direction times the time interval. And so, as I said, for part B, I want to solve for the force on the ball from the wall, as opposed to what they're asking for. And all we have to do to get that is write this. And this is 2 mv sine theta over delta t, right? And you probably realize this, but just in case you don't, what we have for the average force in the x direction is 0. And I'm not going to write this in unit vector notation because specifying the components, right, is perfectly equivalent, in my opinion. And so you might be wondering what this would look like if we wanted to solve for what they actually ask for, right, which is the average force on the wall from the ball. And the way you would do this is you would just remember what Newton's third law says, right? And so the magnitude of the force that the ball exerts on the wall is the same as the magnitude of the force that the wall exerts on the ball, but they just point in opposite directions. So if you wanted to actually solve for what they were saying, for what they're asking for here, it would be the same result that we found for F sub y bar, but you would just put a negative sign in front. And so hopefully that's clear, but feel free, of course, to reach out if you have any questions about this. And hopefully this is helping to make these ideas about momentum and impulse and the force a little bit clearer. Okay, so I'm going to clear my screen here. And let's move on to the next one. Okay, so a steel ball, well, this is number 64, also from chapter 9, right? And a steel ball of mass ½ kilogram is fastened to a cord that is 70 centimeters long and fixed at the far end. The ball is then released when the cord is horizontal. At the bottom of its path, the ball strikes a 2.5 kilogram steel block initially at rest on a frictionless surface. The collision is elastic. So that means we can apply conservation of energy, right? So we want to find the speed of the ball and the speed of the block both just after the collision. Okay, so to do this, we need to figure out what the speed of the ball is before the collision, right? And well, actually before I do that, let me of course do the usual thing. Say that the mass of the ball is little m, and that is ½ kilogram. The length of the cord is 70 centimeters, or 0.700 meters. And here's where there's something interesting, right? The mass of the block is 2.5 kilograms. But this just so happens to be 5 times the mass of the ball, right? And you'll see why I'm stressing this and why this is a nice thing to know as we get a little bit deeper into the problem. But I want you to remember that the mass of the block is simply 5 times the mass of the ball, okay? Because I think before we get there, I'll probably have to clear my screen again, right? So the first thing to do is to figure out the speed or the velocity, right? Because we can just kind of look at the picture and probably realize that the velocity is going to point to the right for the ball right before it hits the block. And we're going to do this using conservation of energy. So what we have is we have, let's say, E initial equals E1. And if this is L, and we define our y equals 0 to be about here, which is perfectly fine. Of course, remember, we can always decide to do that wherever we want for gravitational potential energy. What we have is we have that the initial mechanical energy of the system is just mgl, right? And then since we're thinking about right before the ball collides with the block, the only mechanical energy at that instant will be the kinetic energy of the ball, which is going to be 1/2 m, and I'll call it u naught squared. So this shouldn't be anything surprising because this is the result that we would get from kinematics, right? We can cancel the m's, and we find that u naught equals the square root of 2gl. Cool. So what we want to do is then look at the momentum and energy. So I'm going to use subscripts that don't exactly correspond to what I've written so far. but I can't really see an easier way or a clearer way of doing this. So note that when I write this next set of equations, the subscripts aren't the same. Because usually the subscripts, represent like a point in time, right? And they're not going to exactly line up with what we just did. So now we're thinking about, let me draw a dotted line here, maybe just to indicate that this is a new sort of train of thought. Now what we're doing is we're looking at the situation right before the ball collides with the block and then right after. So we could do something like this. We could say, well, we know that our initial momentum is going to equal our final momentum, and they tell us it's an elastic collision, so we know that our initial energy is going to equal our final energy. So what do we have as far as the momentum goes before the collision? Well, it's just the momentum of the ball, right? And that, remember, is mu naught, but we already found u naught, so I'm just going to substitute in square root of 2gl right away. Okay. Let's look at what the energy is. The energy is just kinetic, and it's going to be 1/2 m u naught squared. So that is 1/2 m, and u naught squared is just 2gl. Okay. And let's fill this in since we're here already. We're going to have that the final energy is also just kinetic because this is all happening now basically on flat ground. And so this looks like the kinetic energy of the ball just after the collision, which we could write like that, plus the kinetic energy of the block just after the collision. And notice that I'm doing this thing where I use a u to indicate the speed of the ball and a v to indicate the speed of the block. So now let's fill this other side in for momentum. So now it's kind of like you have to make, well, you don't have to, right? If you were told which way the ball was going to go after it hit the block, right? Because it could bounce back to the left or it could keep going to the right. And we don't know. So the safest thing to write here is just mu plus big M V. And when we go through and solve this system of equations, because note that we now have two equations and two unknowns. So these are my unknowns, and then also same unknowns, right? And you might be thinking, well, like, wow, this looks like it's going to be some disgusting algebra, and yes, it unfortunately will be, right? But I do want to show you one way that we can simplify it. So I'm going to get rid of this up here and show you a way that you can simplify it a little bit. It's still not going to be necessarily fast and easy, but this will help a bit. And it's something I want you to keep an eye out for, right? So we're just going to rewrite our equations, the equations that we want to solve, because now it's just a math problem. So the first equation came from conservation of momentum. Okay, so we had m square root 2gl equals mu. But what I'm going to write now is, remember we said that the mass of the block is 5 times the mass of the ball. So here what we can write is 5 mv, like that. And the mass goes away. We can just cancel that right out. So that is a little bit helpful. And then let's do the same thing for the energy equation. Well, 1/2 m times 2gl is just mgl. Probably not surprising, because that was our initial energy. And then we have 1/2 m u squared plus 1/2 5m now v squared. Because again, the mass of the block is 5 times the mass of the ball. And so we can go ahead and cancel the mass from this equation as well. And at this point, what I would like to do, I think, is just solve this in Mathematica. And remember, you were, of course, encouraged to use Mathematica or computational software of your choice. I just want you to, like on an assignment or an exam or anything like that, just indicate that you are using it, so I know why you might be skipping the algebra in your work. So I'm going to put this, I'm just doing this on my other monitor here, and it might take a little bit, so just bear with me. Oh, also, I should mention that probably at some point during this video the lights will go out because they're on a timer in the lab and motion activated, so don't be alarmed if it gets dark. Just make sure I put this in correctly. And I will show you now what I obtain. I'll clear this, I guess, so it's not so muddled here. And so because of the squares here, I get two sets of solutions, right? And the only thing really to do is to just evaluate them numerically, I think, and see what we get. And I need the numbers, so let me just see what those were. So, oh, there's no mass dependence. I don't even need that. Cool. So L is 0.7 and G is 9.81. So look, the nice thing about realizing that one of the masses was some integer multiple of the other is we only have like two actual things to plug in, and we find two sets of solutions, right? So this first set here is basically saying that the block has no speed after the collision, which I think we can probably throw out as being unphysical. This is just an artifact of the math. So what is the more realistic solution is that the ball bounces off and now is moving to the left with a speed of 2.5 approximately meters per second, and the block is moving to the right with a speed of 1.2 meters per second. And so I think that I like this solution much more than the other one, numerically speaking. Though mathematically they're all valid, right? It's just now we have to separate the math from the physics. And hopefully we all agree that this set of solutions is the one that makes physical sense. And I mean, it has to be, right? Because there's no way the ball could continue to be moving to the right with a speed of 3.7 meters per second and the block not be moving at all, right? I mean, the ball isn't just going to, pass through the block, right? So it seems pretty likely that this is the solution set that we want. Cool. Now, for those of you who would want to do the algebra by hand, the first thing I say is why. But being serious, the way you would do that is you would just make a substitution, right? You would solve your momentum equation for either U or V, and then you plug that into your energy equation, and then you just crank out the math, and you should find the same thing that we found. Okay, let's move on to the next one here. This is number 73, again from chapter 9, and we're not given very much here, actually, no numbers. which personally I love. But we can still actually get a numerical value for this. So the problem says after a completely inelastic collision, right? Remember, that's a collision where two objects collide and then stick together and move as one. Two objects of the same mass and same initial speed move away together at half their initial speed. Find the angle between the initial velocities of the objects. And so here, as I said, we're not given a lot to grab onto, but in some ways that's nice because we can just make some simplifying assumptions that are valid physically, and everything's going to be okay. So what I want to do is actually start with a sketch here. And so maybe we can visualize this like this. So I'm going to think about this as being, well, I'm going to think of this as happening such that after the two objects collide, they move in the x direction. And this is fine because we can always assign our x direction such that this is true, right? Like if you imagine that this is happening and say, it's not, say you're looking at it from above and it doesn't look perfectly horizontal, well, you could just twist your head so that it does, right? So let me make a sketch here. And this is going to be one of the masses. This is going to be the other. And let's say that this one has velocity vector v, and this one has velocity vector u. And I'm going to call this angle theta, and this angle is also theta. And what we want to solve here for is 2 theta, basically, because if we imagine that they're right on top of each other, right, that is these two vectors, what we have is something like this. V, U, and then theta here and theta there, right? So the angle between them is 2 theta. I'm going to erase this though, because I don't want to clutter up the drawing too much. And so now let's come back to our sketch of what's actually happening. And remember, we said that now we have a mass, a combined mass of 2m, and they're moving in what we choose to be the x direction with some velocity vector, and I'll call it big V. Okay, so we probably suspect that this has to be entirely done via conservation of momentum because it says the collision is inelastic, and that means we can't apply conservation of energy. So let's see what our momentum equations look like. We write out the momentum of the system in the x direction. This is m, let's see here, mu cosine theta plus mv cosine theta. But remember that they have the same initial speed, and the reason that I didn't call both of the initial vectors u or both of them v is because it would be sloppy, right, since they aren't the same vector. They have the same magnitude but different orientation. So I'm trying to be a good example, not be sloppy. And so, but when we're talking about just the components, that means we can just say, well, let's say this is also little v. I don't want to do that actually. I want to use u. So let's say that this is u. And this is just so you can look at our final result and see the difference between the v's, right? So this becomes 2mu cosine of theta. And the final momentum of the system in the x direction is just 2m big V. Now we can write out the momentum in the y direction, and we'll do that just for practice, but I don't think we actually will end up needing it. But what this would look like is, for the mass that I've drawn on top, negative mu sine theta plus mv. Oops, hang on. Okay, cool, we're good. mv sine theta. I accidentally pressed the home button. mv sine theta. And this is just 0. Because again, u equals v, right? The magnitude of the vector u is equal to the magnitude of the vector v. So that's cool. And we find that the final y momentum is also 0, right? Because as we have chosen this, or as we've chosen to think about this, the mass, the combined mass, has no y component of velocity. So this doesn't really do anything for us. So let's focus on the x direction though, because this will help us. Oh, and we're told that they move together at half their initial speed, right? So what that means is that the magnitude of big V is just u over 2, which is also little v over 2, right? So we'll plug that in now. Now we're looking at the conservation of momentum in the x direction, and we can write 2 mu cosine theta equals 2m, and remember big V is 1/2 u, so we can write this u over 2. Now we get a good amount of cancellation here, right? This 2m cancels, this u cancels, and we find our equation just says that cosine of theta is 1/2. Now, I happen to know that the cosine of theta being 1/2 implies that theta should be 60 degrees, right? But you could arc cosine this and figure that out, right? Without too much work, I think. So let's just say theta equals 60 degrees. But remember, what we wanted was the angle between the velocity vectors, whereas what we're calling theta here is the angle the velocity vector makes with the positive x-axis, right? Above or below. So very last thing to do is just say, well, let's define big theta. That's what this is supposed to be. Big theta should look like that, maybe. And we define this to be double little theta. So the answer is 120 degrees. But I think you can see that solving for little theta was really integral to obtaining the answer here. And once you get little theta, you've basically solved the problem. Okay, cool. So I guess the lesson here is, like, we can do a lot even if we're not given any numerical values. I think it's a good lesson. So I'm going to clear my screen here and we'll move on to the very last problem. Let's see what I chose. Okay, so in the figure, a 10-gram bullet moving directly upward at 1,000 meters per second strikes and passes through the center of mass of a 5-kilogram block initially at rest. The bullet emerges from the block moving directly upward at 400 meters per second. To what maximum height does the block then rise above its initial position? So this is going to be a problem where we start out with conservation of momentum, and then we use what we get from applying conservation of energy or momentum to apply conservation of energy. So let me just say some stuff. I'm going to say that the mass of the bullet is little m. That is 10 grams. So remember, we divide this by 1,000 to get it into kilograms, and it should be 0.01 kilograms. What is this doing here? You say 0.01 kilograms. Yeah. And then I'm going to say, why does it Oh, you can't even see that, but on the tablet an S keeps appearing, and I just erased it. This is like very strange. Okay. Anyway, so we'll say that U initial for the bullet is 1,000 meters per second. Okay, the mass of the block is big M, and that's 5 kilograms. And then we're told that the speed of the bullet after it passes through the block is 400 meters per second. Okay, so we're going to do conservation of momentum in the y direction. And we're going to think about like right before the bullet hits the block and then immediately after it emerges from the block. And so what we'll have is the initial momentum is just m u naught. Now notice here that there's nothing in the problem statement that indicates they're moving together, and actually there's something in the problem statement that indicates they're not moving together, and that is where it says the bullet emerges from the block. And so we have to do this. We have to write the sum of the individual momenta, right? So what this ends up looking like is little mu plus, and then I'll say big M v. So v is going to represent the speed of the block after the bullet emerges from it. And so this is just a matter of solving for v, right? So mv, rearranging the equation, we find mv equals m u initial minus mu, and therefore v is just m u initial minus u over big M. Maybe just check this to make sure it looks good. Yeah, I think that's fine. Okay, cool. So now we just focus on the block. And I swear that I'm not insane, but this damn S is appearing again. Okay, I just erased it. Anyway, so now we can just focus on the energy of the block by itself. And this is us choosing our system, defining our system now after the bullet has emerged from the block to be just the block. And this is legal because the energy of each component of our system should be conserved separately as long as they're not interacting, right? And hopefully that makes sense. So now again, I'm going to do this thing where the subscripts don't line up, but I'm going to say E initial equals E final, and remember this is just for the block. And actually you could, you know what, we could include the bullet. Or actually, I don't think we have enough information, but maybe I'll talk about what it would look like if we include the bullet after we solve this. So now, if we define our y equals 0 to be right at the center of mass of the block, which is the most sensible choice, then the only initial energy that the block has is 1/2 big M v squared. And then when it's at its maximum height, all of the kinetic energy is converted to gravitational potential energy, right? So we could write this. And the masses cancel, and we find H to be v squared over 2g. And this should actually look familiar from kinematics, right? And so going ahead and plugging in what we know v to be, which is what we found over here on the left, we find that this is m squared u naught minus u quantity squared over 2g big M squared. And that's your answer, right? This is how high the block goes. And for you numbers people, of course, you can plug the numbers in and see that you get something reasonable, right? You probably wouldn't expect it to go terribly high, because you can imagine this happening in real life, and you might think the block like probably goes up a couple feet or something, right? So just look at the numerical value that you end up obtaining and see if it seems reasonable. So probably before I end the video, maybe just because I did mention it, maybe we can talk about just generally, right, what the conservation of energy equation would look like if we included the bullet. So let's do that. I think I want to clear the whole screen here, because this will just be sort of conceptual. So remember that we're defining our y equals 0 to be the center of mass of the block. And incidentally, center of mass is something that is typically discussed at the beginning of the unit on linear momentum, but I'm actually going to postpone that till we talk about torque. So we will get to that topic, it's just not as of right now. And so let's look at, let me make a sketch here of what we're talking about, right? So we're looking at the energy like right after the bullet has just emerged from the block. And this, remember, is moving up with velocity u, and the block is moving up with velocity v. So the energy here would be the kinetic energy of the block plus the kinetic energy of the bullet. And we would need to know, right, how high the block is, or the bullet rather, sorry. We would need to know how high the bullet is above our y equals 0, which remember is this. And so we could say that maybe the height of the bullet is y equals, and I'll make, how do I want to do this? I guess we'll just call it like script y, because we're going to have to use h in the other part. So what I would do then is I would write here, I would write little m g script y. And that is the gravitational potential energy of the bullet. And notice that we're already kind of running into an issue here, because we don't know how high it is. Like if we knew the dimensions that the block say, then we could write something about this, but we don't. We don't know the height or width or anything about the block. And then the final energy, though, is going to be, let's see here. Now we're talking about the energy when the block has reached its maximum height above the y equals 0 position. And that's going to just be, by our choice of notation, mgh. Now, we know from our ideas about kinematics that the speed of the bullet will have decreased, right? Because time will have gone by. We don't know how much, but time will have gone by. I guess we could solve for how much time has gone by, but we don't really need to. And so we know that the speed of the bullet will have decreased. So what I could write here is for the kinetic energy of the bullet now, is that it's 1/2 m, and then we could write something like u minus delta U quantity squared for the kinetic energy of the bullet, just to show that it has decreased. And then similarly for the gravitational potential energy of the bullet, we know that it's going to continue to rise up into the air, right? So for the gravitational potential energy, we could write something like mg script y plus delta script y. But notice that this is introducing a lot of things to solve for, or a lot of variables that we don't really even know the value of. Like I said before, we don't know what this is. And that's going to create a problem because we can't define for the bullet and block system, we can't define y equals 0 to simultaneously be at the center of mass of the block and at the y position at which the bullet emerges from the block, right? That's just totally inconsistent. We just can't do it. And so what we do is we just say that the block's energy must be conserved and the bullet's energy must be conserved separately, right? Of course they're conserved together, but they're also conserved individually, which is why to solve this we can just, for the height that the block attains, we can just kind of get rid of this and rid of this, and it still works for us, right? I just wanted to discuss this because I could anticipate some people potentially getting confused by it, and if you were one of those people, that's good. I mean, it shows that you're thinking about this stuff, right, deeply, and I am absolutely all about that, but hopefully I've convinced you that in the end it didn't matter, okay? So hopefully you found this helpful. Feel free, of course, to reach out if you have any questions about anything that was done here. You can email me or you can ask during our weekly meeting, but hopefully this was useful, and I will see you in the next video.